So batteries are ubiquitous devices that are in our everyday life, from our smartphones to our smartwatch, electric cars. They're everywhere. However, we don't understand them at a very low level. And part of that complexity is because when they tend to age, as we all know, batteries tend to age. We have to change our smartphone every 2 years. So when they tend to age, the dynamics, the internal dynamics of the model of the battery change. And this is pretty hard to capture. In this work that was done in collaboration between the CSEM, ETH, Zurich, NASA, and EPFL, we explore and we propose a new method, which is kind of calibration-free, so it doesn't need to be calibrated, to kind of capture this change in dynamics and really understand what is going on in the battery in making accurate forecastings. So let me formalize a bit more our task. We have on the top of this image, we have some current profiles. And ideally, our goal is, given this current profile, we want to predict how does the battery behave. So we want to predict the voltage, the output voltage profile from the given this blue curve. Naively, we could ignore completely the aging, but then, as I will show in the next slide, this will lead to poor performance. Taking into account that also this current profile can have any type of profile. We don't know in advance how the user is going to use the battery, and especially in mission-critical application, it's hard to tell how is going to look this current profile. So we want to make something that is really generable and it's easy to be used. So as I was saying, the batteries are also affected by aging, and here I have two nice plots that shows that given the same current profile that I was showing before, like changing some internal characteristic of the battery, which change naturally when the battery is aging, tends to change dramatically the output of voltage. On the left picture, you can see how basically when changing the number of charge in the battery, the total length of the profile decreases, so the battery lasts less. And on the right, you can see that if the internal resistance of the battery increases, which again happens when the battery is aging, the voltage starts from a lower place. So again, our goal is kind of, can we come up with a method that can take this into account and then give our voltage profile accurately? And we started with an intuition. We were thinking a bit about the fact that if these parameters kind of affect the output, so you can kind of see them doing something on the voltage profile, maybe we could train some sort of nice encoder, some nice approach that, given just a tiny small window from the beginning of the profile, we could do some of the reverse process. So we could kind of inverse the problem and say, okay, given like the pair of profile and voltage, just from the very beginning of the profile of your curve, can we infer these parameters? And we came up with this encoder. Of course, now the question was kind of, how do we train this? Because if it is supervised, then you will need to have access to these internal parameters, which typically they are like hard to measure. You will need to open the battery, and you don't want to do that. And then how would we condition this encoder to the rest of the architecture? So how can we use this information then to output the voltage profile? And our answer was kind of this kind of novel architecture we're proposing. We call it Dynaformer because it's kind of totally inspired to transformers and to vision transformers, although there are some technical tricks that we use. And the idea is that we train end-to-end, so we don't need those parameters eventually. We can just train end-to-end a network that takes as input a current profile and outputs this voltage profile. And it is conditioned on this encoder output, which in turn it takes as input just the very first part of the curve. And the cool thing about this approach is that the decoder, which is kind of a transformer, doesn't need to know anything about those parameters, but there is kind of without any strong supervision, this will naturally be the parameters that you're looking for. And as I was saying, we also take inspiration from vision transformers, which is kind of a novel application of a transformer to computer vision. And we use the same approach. Since, as you may know, like transformers have these issues of complexity that grows quadratically, when we are dealing with the voltage and curve profiles, might be that the battery lasts 3, 4, 5 hours. And then this leads to very long time series. And then if we kind of just using like a off-the-shelf transformer, this will not work because the time series is too long and then everything explodes. So what we are doing is kind of doing a chunking approach. So we are chunking each section of the input and the output time series of the current voltage profile in some chunks that we then encode in tokens, and then we feed these tokens to the decoder. So in this way, we can deal with the complexity without losing any information in the resolution. And we tried this approach on a nice library provided by NASA, which is called ProgPy, which is open source. You can all download it. And basically, it's a prognostic library about batteries. It's a simulator. It can generate current and voltage profile, and you have access to the internal parameters. You can kind of synthetically generate curves that will appear in real life. And we were training our model just on synthetic data, and then we tested both on some out of sample test data, and then we also tried to test it on real cases. And what we saw was basically qualitatively that the results are actually really nice. So as you can see in this plot, there are basically two curves for each plot. One is the dashed line, which is kind of the ground truth of the voltage profile, and the blue line is what the transformer is outputting, given just information of the input current profile, which qualitatively it's really nice because it's kind of overlapping completely. So our network is able to kind of learn this mapping from the current, given the condition, to output the voltage. We did some more quantitative analysis, and we compared this method against kind of off-the-shelf or baselines, as for instance LSTM and FNN. We could not use the off-the-shelf version of the transformer for the memory complexity issue I was mentioning before, so you could not train it. And what you can see is basically that our method kind of outperforms substantially the other baselines. And without going too much in detail of the meaning of the metric, you can see that pretty much there is a big gap from the other baseline, which is remarkable. And also the extrapolation performance are slightly worse than interpolation performance, but they're still good, meaning there is a good generalization performance. And we study a bit this generalization performance, and we were wondering how is the model behaving to different kind of inputs. And the first test we did was kind of, okay, let's train our model just with kind of this stepwise function that you can see here in the blue line. So it's, we'll just show it here. Doesn't work, but it's just those blue figure. And as you can see, there are stepwise function, and we were kind of training to up, I think, 5 stepwise, so you have a maximum 5 steps. And then in the test, we were increasing this up to 11. And we were studying, as you can see on the right plot, how the performance decreases. And you can see that, of course, there is kind of a tendency of decreasing performance, but also with the kind of profiles above 5, which was within the training set, the performance do not explode and do not become suddenly worse, but the model is quite robust to this kind of unseen input profile, which is kind of nice. And then we study a bit the generalization performance in terms of the conditioning. So we had two kind of degrees of freedom. The first was kind of what input are we giving to the model, and the other one, how old is the battery that correspond to that input and output is. And what you can see is pretty much that in this picture, the black square is where our training range lies. So all these dots, each dot represent a run of a battery, kind of represent a training sample. And you can see that performance are quite nice because it's almost white. So white means the error it's almost 0. And then outside, you have the extrapolation range. And again, as you can see, there is like a deterioration, of course, but it's not so abruptly. The two plots represent two different current profiles. So we were studying, we were kind of iterating over all the different battery configuration in terms of aging possible with two different current profiles. You can see on the left and on the right. And so the performance also with unseen aging conditions do not explode and do not become worse instantly, but there is kind of a nice smoothness, which is kind of something that in a deployment you kind of require, because you cannot imagine of training your simulator just using data that is what you expect in real life. So it's kind of this robustness to aging is also quite interesting. Jumping to the next slide, I think this is quite interesting. We studied a bit how does the embedding out of the encoder look like. So as I was saying, we train our network without using any additional information about the aging or any parameter of the battery beside of current and voltage. But what we found out was essentially if you are doing a PCA, a principal component analysis on the output of the embedding, you can pretty see that this is kind of consistent with the values of the internal battery. So on the left, pretty much you can see kind of we're plotting for each dot represent again a run, and we're representing kind of what is the number of charge inside that battery. And you can see that it's not like an inhomogeneous plot, but there is a kind of consistency. So there is kind of a gradient, means that the principal component here is kind of correlates strongly with this internal characteristic of the battery. And on the right side, we are doing it for another internal parameter of the battery, which we had access in this case because it was simulated for comparison purpose. But again, you can see this strong correlation. So kind of the takeaway here is that the model learns kind of how the battery behaves and all the internal physics with just a weak supervision, because it just have current and voltages, which is quite nice. Then I was saying we also apply the model on real data, and we stumble upon an issue here. So the model we were using from the simulator we're using, although it's quite good, it's not perfect, and pretty much there is a small bump between, there is kind of a simulation to real gap, as you can see in the bump on the left plot. You basically, essentially you can see that the dashed line represents what the simulator data look like, and then if we have exactly the same curve from a real battery, then you will have the real data line. So it means that the model itself does not capture the entire complexity of the real data. And of course, when we train only on synthetic data, our model doesn't have any clue about this gap, and at first, without any kind of transfer learning technique, what happens is that the model performs not extremely poorly, but it doesn't perform as well as in the synthetic curves. However, then we decide to try this very famous transfer learning technique of just fine-tuning our model trained on synthetic data on real data for a small number of iterations. And what happens, which was quite interesting, is that you have the model closing this sim to real gap without forgetting about all the dynamics, all the important physics that was learned before. So that's super nice that the model does not overfit on the real curve. So it preserves the physics and all the priors and bias that has learned by the model, but still closes the gap. And you can see pretty much on the right figure where we're showing how does the output of the network is looking at before and after fine-tuning. We also did a quantitative study about these real curves. So NASA has a data set of around, I think was around 80 real batteries. So we had like this kind of nice data set to test on. And we used some of these curves for training and some of this curve for actually testing. So we did this analysis of saying, okay, how does the performance improve when we are fine-tuning with more and more real curves? And you can see that after even like 20 real samples, the model already reached a performance which is almost in line with what was reached in the synthetic scenario. So we reach an error of 0.03, so it's 3%. And you can see that really like a small number of real curves allows the model to kind of performs good on real data as well. And this is kind of nice that our network, which kind of resembles a transformer, maintains all the nice properties of a transformer so that you can do transfer learning with them and fine-tune them. So it's kind of nice that all these properties, also about generalization that I was showing before, are preserved in our model. And I just want to conclude saying that I think this is the first approach, calibration free. So we're not using any calibration to do an end-to-end highly accurate prediction of the end of discharge and the entire voltage curve. We have, as I show, good generalization performances. And we have this kind of nice interpretability without ever needing the need of training on data from that are from the battery beside current and voltage. And I want to put some emphasis on the fact that now we use this case study about batteries, and we're more than open to try new batteries if anybody else of you has some nice use case or some nice application. But I think the general idea, that's why we call Dynaformer, it's kind of nice, and it's kind of something interdisciplinary, because eventually for any task where you can have a sequencing input and you want to do this kind of transducing approach, and you want an output sequence that is conditioned on something else, as in the battery. The battery, we're going from current, conditioning on aging, and then outputting the voltage. We could apply the same model and the same technique. And I will be honestly very curious to see how it performs, because in this case it works pretty well. Yeah, thank you very much.